Hi, my name is Ming. So I'm an associate professor at Arizona State University. Jorge Cabrera is my PhD student. He's currently on leave. That's the main reason why I'm presenting this work instead of him. So our work is about supporting time-sensitive applications in virtualized computing systems, such as public and private cloud systems. We know that cloud computing has already achieved greater success. Many applications can already be enabled in the cloud. The main reason behind the success of cloud is cost effectiveness, right, scalability. But how about time-sensitive applications? We don't see a lot of success with enabling time-sensitive applications in the cloud. And then when I say time-sensitive, we are mainly considering two types of applications. One type is applications with soft deadlines, and the other type is applications that don't really have deadlines, but they require low latency. They have maybe a tail latency target. So we see that, we believe that the main challenge to supporting these types of applications in the cloud is because the success of cloud is based on resource consolidation, high resource consolidation. And because of the high level or high degree of consolidation, there's complex and dynamic contention among the virtual machines. And time-sensitive workloads are unfortunately particularly vulnerable to this contention. And what makes this problem more difficult for the resource management system is that there's a lack of awareness between the virtual machine host and the virtual machine guests. And to be more specific, the host does not know what kind of applications are running in the guests and what are their requirements, and also the guests do not know the host, the resource allocation, resource management decisions made by the host. Here I use a very simple, almost toy example to illustrate why this lack of awareness creates a problem to support time-sensitive applications. So in this simple example, I just quickly go through it. So we have 3 virtual machines sharing a single CPU, and this Gantt chart shows that we have enough CPU bandwidth to satisfy the bandwidth requirements of all the 3 virtual machines. But if when we look at the 2 time-sensitive applications running on VM1, the way that the diagrams of how these applications are aligned to when the virtual machine is given time to run, will actually make the second application miss every other diagram when it is scheduled. Again, the reason is because even though there's enough bandwidth to satisfy everybody's requirement, but because the host schedule cannot give the virtual machine the application running on the virtual machine the bandwidth when they really need the bandwidth. As a result, they cannot always meet their deadlines. So to solve this problem, our solution is called RTVirt. Our solution is based on 2 levels of work. First, we designed a new virtualization architecture which allows the guest and the host to communicate and cooperate on scheduling. And this cooperation has to be low overhead because we're trying to support fine-grained timeliness requirement. And based on this framework, then we also created new cross-layer schedulers that are able to work together and deliver strong timeliness guarantees. For example, we're able to meet 99% of all the deadlines or support a 99% tail latency target. And when we achieve both these strong timeliness guarantees, we are also able to make efficient resource utilization. Okay, compared to a state-of-the-art related work, we save up to 50% of the CPU bandwidth. So, of course, our solution is not complete. As a first step towards a more complete solution, we have made many assumptions. Our focus is on CPU scheduling. So we support CPU-bound applications, but we do want to support applications with different levels of timeliness requirement, and we also want to support dynamic applications and virtual machines, which means that the application virtual machine, they can come and go at any time, and also their requirements can change at any time. We believe these are very important to applications in the cloud. So I have already introduced the problem background. In the rest of my talk, I will explain the architecture algorithms, scheduling architecture algorithm of RTVirt, experimental evaluation, and finally the conclusions. So in terms of architecture, so we made the decision to keep the existing two levels for schedulers in the virtual machine system. In the existing system, we have the process schedulers in the guest and the virtual machine scheduler at the host in the hypervisor. We decided to keep these two levels of schedulers because we believe that is important for better scalability by separating the concerns of process scheduling from virtual machine scheduling, okay, using the two levels of schedulers. But in order to support time-sensitive applications, we want these two levels to cooperate. Right? That's what we mean by cross-layer scheduling. We want to enable cross-layer communication and cooperation on scheduling. And more specifically, the guest schedulers can inform the host on application timeliness requirements in terms of the bandwidth requirements and deadlines, etc. And the host scheduler can also notify the guest virtual machines that the resource allocation decisions. Now, based on this architecture, okay, so then let's look at the interfaces that we are exposed to different layers in this architecture, okay, on this architecture. So instead of the guest, at the application level, we actually use existing system call interfaces. Okay. For example, on Linux, there's a system call called a set attribute. Okay. That is a system call that an application can use to register itself and its real-time requirements with the operating system process scheduler. So we reuse that scheduler so that we do not make any change, we do not require any change on the applications. So we believe that's very important. So we can support, our solution can support unmodified applications. But at the host level, we use to allow the guest and the host to cooperate on scheduling, right? Then for that, we use a pair virtualization interface. So more specifically, we added a new hypercall that's called RTVirt, and also a new piece of shared memory between the guest and host for sharing critical information. Okay. So by doing that, of course, we are trading complete transparency for improved timeliness. Okay. So our principle is the same as the reason for pair virtualization. Now we are trading transparency for some other aspects of the system. Right? In this case, we are trading transparency for improved timeliness. Now, let's look at the schedulers at the guest level and the host level. The guest level scheduler is actually pretty simple. So we in fact use a simple partitioned ETF scheduler. The only thing I want to emphasize is that instead of using a global ETF scheduler, which is supposed to be optimal than partitioned scheduler, we assign the application to different vCPUs, and our guest level scheduler schedules the processes that are assigned to a particular vCPU. So the processes are not allowed to migrate, and that is good for us because it makes it really easy for us to determine the bandwidth requirement of each vCPU because processes don't migrate. It also helps us avoid the overhead from process migration. But by doing this, we do not sacrifice resource efficiency because the vCPUs are allowed to migrate, okay, and map to different PCPUs. So as a result, we can still achieve nearly full system utilization. So that's the trade-off the decision we made, and it worked out well for us. At the host level, schedule is a lot more complicated than the guest level. So we want our schedule to be optimal. Want to be able to do optimal multiprocessor scheduling. So what that means is that if the total amount of available bandwidth is greater or equal to than the total amount of required bandwidth from all the applications, then we must be able to support schedule all the applications. Okay, that's what it means. So in order to accomplish that, we base our scheduler, our host level scheduler, on a existing optimal multiprocessor scheduler. It's called DPRAP. So DPRAP was created for non-virtualized system we adopted and extended to make it work for virtual machine scheduling and to support cross-layer scheduling. So I don't have time to go into details of DPWrap, but the basic idea of a DPWrap is that it will consider consider all the tasks deadlines as deadlines for everybody, and those are called global deadlines. And the time slice between two consecutive global deadlines is called global slice, and global slice is partitioned among the tasks according to their bandwidth requirements. Okay, that's just basic idea. Now, to make it work for RTVirt, so what we did in this cross-layer version of DPWrap is that the host schedule will use DPWrap to schedule all the vCPUs according to the vCPU's deadlines, okay, and according to vCPU global deadlines. Okay. And then so instead of us using DPWrap schedule processes, we use DPWrap to schedule vCPUs. So the next global deadline is the earliest deadline of all the vCPUs. And then the global slice is the time slice between two consecutive global deadlines from the vCPUs. Okay? And then we partition the global time slice among the vCPUs in the same way how DPWrap works. And then the vCPU's bandwidth requirement is shared with from the guest to the host by using the RTVirt hypercall, and the global deadlines are shared from the guest to the host by using the shared memory. So in summary, this is our design. So we have two levels of schedulers, and they work together. The applications use the existing system call, and no change required. And the guests communicate with the host using hypercall and shared memory. So now let me present our evaluation results. So we did our prototype based on Zen and Linux, and we consider a variety of benchmarks. I will explain them shortly when I present the results. But in summary, we have considered both synthetic applications, which allow us to vary the parameters conveniently, and real-time applications, including both a video streaming server that has a soft deadlines, and also a in-memory data store, memcached, and that has a tail latency target. And we compare to Artisan, that is the state-of-the-art real-time virtual machine scheduler. It is based on the CSA theory, which is a traditional real-time hierarchical scheduling theory. And we also compare to the default Zen schedule, which is created. So I want to spend a little bit of time on the first experiment, although it's based on synthetic benchmark, but it allows us to explore the space, the design space quite conveniently. So here in this graph we show, so first of all, so we in the table we show all the parameters of all the applications that we considered, and the bottom bar graph shows the CPU utilization achieved from RTVirt versus Artisan. And so first of all, both RTVirt and Artisan are able to meet all the deadlines. Okay, so in each group bars, the right bar, with the green shaded bar is from RTVirt, and the gray shaded bar on the left is from Artisan. So the several observations we can make from this result. First, RTVirt is highly resource efficient because compared to the right shaded bar, which is the total bandwidth, the raw bandwidth requirement from all the applications, RTVirt requires just a little bit more than what the applications really is. Okay, so our overhead in terms of resource utilization is really low. And then compared to the gray bars, which is the amount of bandwidth that needs to be set aside for real-time applications in the Artisan solution, we can save up to almost 40% of our CPU bandwidth. All right, so let me very quickly go through the next of two experiments. The second experiment is we want to study how we can support dynamic applications. So we use video streaming servers. Just forget about this chart, that's too complicated to explain. But in general, we run a total of 54 streaming servers, and they came at different times, and also left at different times, and their bandwidth requirements were also set dynamically. Okay. And this kind of scenarios cannot be supported by Artisan or other existing works, but we can support it really well. Out of all the 54 streaming servers, only 5 of them had data misses, and at the most 0.1% misses. And this is the last experiment I want to explain. This is also important because here this is an application that does not have dial lines but have a tail density target. And so we compare to two different artisan configurations. Only one of the two is able to meet that tail density target. And we also compare to credit. And credit is interesting because credit actually delivers the best average latency, but it misses the tail density target miserably. Okay. So overall, this experiment shows that RTVirt is able to meet the tail latency target and save 50% CPU bandwidth compared to the artisan configuration that actually works. All right, so I skip scalability. So now there are a number of related works where absolutely not the first one studying this problem. I already mentioned artisan is quite pessimistic and does not support dynamic applications. There are also works that took the cross-layer scheduling approach, and which were published before. And in those two works, they consider only simple host-level scheduler, and which is not optimal, and they also cannot support dynamic applications. Finally, to conclude, so we feel that supporting strong quality of service in general is still an open problem in cloud computing research. And in this work, we focus on the strong timeliness guarantees, okay, for the software real-time applications and the latency sensitive applications with the efficient resource utilization. And in summary, RTVirt is by doing cross-layer scheduling is able to meet 99% of the lines or meet a 99.9% tail latency target, and it can support diverse CPU-bound applications with in a dynamic environment. And there are, of course, many future research opportunities. First, we want to consider other important resources such as I/O, and also we can consider end-to-end timeliness guarantees across multiple hosts. Right. So I want to acknowledge the sponsors, my team, and thank you so much for your attention. And our code is also open source.
What's your resource management model? Or put differently, if I have a VM on your cloud, can I just monopolize the processor by saying always I have very tight deadlines?
Yeah, that's a very good question, yes. So first of all, we do have a limit on how small your deadline can be. Okay? So that limit in our implementation is 250 microseconds. Okay? So you cannot go lower than that. That will help us solve that problem partially. And also we think that for in the cloud computing environment, right, it doesn't help the users to claim more than what they really need, right? Because you have to pay for what you claim, not what you actually need, right?
Okay, but can you charge for timeliness? Do you have a model for doing that?
I'm sorry?
Do you have a model for charging for timeliness? I mean, if I...
Yeah, right. So that will be the next level question. If this is adopted in the real cloud environment, then we can do that, yes.
What's the motivation for using a global optimal scheduler? Because those are known to incur quite some overheads and not scale so well. And in addition to that, have you looked at peak throughput under RTVirt and the baselines?
Peak throughput. So just because the fact that we can support more, so that's just the experiment I skipped. That's a scalability experiment. So we consider 100 real-time applications, and we are able to support more than artisan. Right? So that tells us that we can achieve higher. So we have support up to 100, and I think the detail in the paper, artisan can support up to 90. Right? So we achieve at least 10% more throughput than artisan. Okay? And so scalability, I think, is also a relative term. So for us, we are able to support up to 100 real-time applications. Maybe a couple of hundred applications should be okay. So that tells us, using a optimal multiprocessor scheduler is okay for our, at least in this context. Yeah, of course, if I go for even larger numbers, thousands of applications, we haven't tried that yet, and I'm sure there will be challenges. Yeah. Thank you.